Okay, well, welcome everyone. I want to get started. We're just a couple minutes behind. So thank you for coming for this week's CSDE seminar. We're so happy to welcome Dr. Schmertmann, who's here with us today. So we'd also like to extend our thanks to Dr. John Wakefield, who invited Dr. Schmertmann and will be our host moderator today. So thank you for that. And let me just tell you that Dr. Wakefield, for those of you who don't already know him, is a professor of statistics and biostatistics here at the University of Washington. So again, thank you, and I'll let Dr. Wakefield tell you more about Dr. Schmertmann. So I will just remind everyone to please use the Q&A. So don't use the chat, but use the Q&A, and please put your questions in as you think of them. That's totally fine to have them sitting in there. You can also just say you have a question, and that would be fine. And at the end, after the talk, we will go through questions one by one, and I will unmute you. So please do read your question. We'd love to hear your voice and have more interaction with the group. And so also we do have the student meeting that will occur following the talk, and that will be led by Jessica Godwin. So we will put the link in the chat for that, but not use the chat otherwise. So I think that those are all my reminders. So thank you again. I will turn it over to Dr. Wakefield.
Great, thank you, Maria, and thanks, Carl. So welcome everyone to today's CSDE seminar. It's a great pleasure to introduce Carl Schmertmann, who's professor of Florida State University and director of the Center for Demography and Population Health. So when I first started getting into statistical demography, 7 or 8 years ago, I quickly became aware of Carl's work and be very inspired by it. He's published in a wide range of topics, including small error estimation, migration, and fertility, and has written papers in both the top demography and the top statistical journals, which is a very rare feat. I think he had a very interesting background. So Carl, after getting a BS in econ from University of Wisconsin in Madison, and then he got a PhD from Berkeley in econ, he spent a couple of years in the Congressional Budget Office, and then had visiting academic positions in Belo Horizonte in Brazil, and then Berkeley in the US. And then he took a position at Florida State University, I believe in 1990, and he's been there ever since. Along the way, he's received a number of fellowships and awards, and was editor-in-chief of demographic research from 2012 to 2018. Personally, I'd like to thank Carl. He's already he's doing a lot of time with us today, so he spent over an hour with my working group from 11 this morning. So I really appreciate that. I really enjoyed that chat we had when he listened to what my working group was, different problems, and that was just very enjoyable. So thanks for that. I won't say I think Maria's explained all the logistics. So without further ado, let's get going. So the title of Carl's talk is Estimating Total Fertility from the Shape of the Age Pyramid, Bayesian Models and Applications. Thanks, Carl.
Thanks very much, John. That's a really nice introduction. I want to thank everybody for coming. I'm very happy to be participating virtually in the seminar. I told John's group I was actually physically in Seattle 4 or 5 years ago to present the seminar. And some of the themes were the same. One thing I want to highlight from the beginning is using these large data sets like the Human Fertility Database, Human Mortality Database, to develop priors for Bayesian models. That's something you'll see several places in today's talk. This material is not super new. We had Matt Hauer, the second referenced author here, and I had a paper in demography last year on this topic. Martha Azevedo and Joe Potter are co-authors on a long suffering and still unpublished paper about indigenous fertility in Brazil. For various logistical reasons, we've had some trouble finishing it. But the application to Brazil was the original reason for thinking of this modeling framework, trying to estimate the total fertility rate using only basic data on the age and sex of the population. Sorry, I'm trying to advance my slide. It didn't work. Okay, why bother doing this? Well, basically because we don't have the data we need very often. Standard estimators need births by mother's age. That's the red A in the numerator in all of those age-specific birth rates. And we sometimes don't have it. So we might not have numerators because we don't have any vital records at all about births. That would be true in historical Europe. It's true in some places in sub-Saharan Africa today. It's true in some parts of Brazil today, that we don't necessarily have complete birth registration that includes mothers' ages, and then we need it for TFR. We might have cases where there are privacy restrictions on releasing the data by mother's age. I'll do one example later. Taliaferro County is the smallest one in Georgia, and NCHS doesn't publish birth rates for that county because it's too small. And then maybe most importantly of all, or most interestingly of all, for using this method we're going to develop, we might care about populations that aren't recorded on birth certificates. You know, what's your income decile, what's your religion, and so on. So the motivation for thinking about other ways of estimating TFR is precisely because of this missing, masked, or defective data. Okay. Here's the age pyramid for the United States in 1968. I'm in it, actually. I'm over here. I think I was 5 to 9 then. It looks like high fertility. Was it? Let's think this out. We've got children 0 to 4, and we've got the potential. Oh, sorry. For some reason, the women are blue here. I forgot that. These are the potential mothers. These are the births. We want to get sort of more technical and demographic. These are the survivors of the births that happened between 1964 and 68. These are the survivors of the potential mothers. And we want to think about how are these related in a sort of careful, principled demographic model. So the way we need to do this is in multiple steps. Derive the relationships between the rungs of the age pyramid, so to speak. Calibrate a parametric model that includes TFR and other things that might affect survival and the relationship between the rungs of the ladder, so to speak. And then third, once we've done that, look at the posterior distribution of TFR. And effectively what we're asking is how plausible are different TFRs given the data we have on age and sex, and given the possible values of things like survival or age patterns of fertility. Okay, for the US, it turns out we can do pretty well. I mean, this is jumping ahead to the method or the answer before you've seen the method. We get it pretty right. This is a fairly narrow range of values covered by a fairly wide probability interval, and it turns out 2.9 was about the US TFR in that period. So I start off with sort of a good case where we get it right. Okay, let's take those steps in order. First, we want to think about the mathematical relationships. Here's a mini Lexis diagram. Think of 1964 through the very first day of 1969. The standard approach is to think of the women who were alive at ages 20 to 24.999 at the beginning of the period. Think about that as some multiple of a life table big L. Think about the number who are going to survive to the end of the interval as a multiple of the same multiple of a different big L. Then think about the exposure of those women to age 20 to 24 fertility rates and age 25 to 29 fertility rates over the period. I won't belabor this, but it's a sort of weighted average, about 2.5 years at the first rate and about 2.5 at the second, but weighted by potential mortality. A standard Leslie matrix or population projection term divides this birth total by the beginning number, which is births per initial 24-year-old. That's how you do a projection. You'd say, all right, here's the number we know are in this age group. Here are the rates we expect. Here's how many births we expect and how many survivors we expect. But what we're going to do here is we're going to do expected births per survivor. As I'm going to think about the end of the period. We know how many women are in the age pyramid in January 1st, 69, right? We want to think about how many births per each of those we might expect. And that's just another demographic accounting term, which I'm not going to belabor. I assume, Maria, this is recorded, correct? Okay, I'm going to assume it's recorded.
Yes, that's correct. Everyone.
Okay, so that gives me license to go a little bit faster, which is good. Sorry, okay, so here's expected births per surviving 25 to 29-year-old. That's what we just saw. We know as demographers what fraction of those births we expect to survive. That's 5L0 over 5. I'll call that S0. So the expected surviving children per woman in the 25 to 29 group is this expression here. It's just S0 times that. And I'm going to call that K25. That's the expected number of surviving kids per surviving 25 to 29-year-old. And of course, we can do this for every age group, per surviving 15 to 19-year-old, per surviving 20 to 24-year-old, and so on. Okay. Another aspect we have to think about is how much of the fertility, of the lifetime fertility that women are ever going to have happened in the last 5 years before we looked at the age pyramid. And for that, I'll sort of invent a quickie notation. I'll call phi 15 is the fraction of lifetime fertility that we think happens in the first age group, 15 to 19. Phi 45 is the fraction of lifetime fertility we expect in the final age group, 45 to 49. Those fractions add up to 1, and we're going to model those fractions. Okay. Oh, and another, I guess that's another aspect of this, is that the fertility rate can be expressed in terms of those fractions as TFR times phi over 5. Okay, so back to our kids per surviving woman. This is the same measure we had before. And write that in terms of these lifetime fractions phi. F20, for example, is TFR times phi 20 over 5. F25 is TFR times phi 25 over 5. Again, I'm not going to, I realize I'm going too fast for this, but I want to get the main idea here, which is the following, that the surviving kids per surviving 25 to 29-year-old can be written in terms of 3 factors. What percent of births survive? That's going to be nearly 1 in rich country populations. Lifetime fertility, and then this sort of weighted average of the fraction of lifetime fertility that happens in the first age group that the women are passing through, and the fraction in the second age group. And what that really is the percent of lifetime fertility experienced in the last 5 years, with a little bit of subtle mortality weight. But there are these 3 factors: survival of kids, lifetime fertility, and fraction of lifetime fertility that would have been experienced by those in this age group over the last 5 years. Okay, so that depends on 2 things that are common across age groups: the TFR and the child survival. And it depends on the age pattern of fertility that shows up in those P terms, right? How much of the fertility is experienced in the last 5 years, and what are the mortality weights that we need to put on that. Okay. So what we need are statistical stories, parametric models, to describe what the big L's are in the mortality weights we need and the fertility weights that we need. For the mortality part, I'm going to use the Wilmuth log Q model. I don't know if everybody's familiar with this, but what I want to highlight here is that it's just a bunch of patterns that were discovered in the human mortality database. Okay, so it turns out you can express the log mortality rate for an age group in terms of 4 constants, A, B, C, D, which are estimated in advance. And then you can plug in a log of the under 5 mortality rate, the log of the under 5 mortality rate squared, and a shape factor that they call K. And K is typically between -2 and +2 in in observed data. Okay, so once you have two parameters, Q5 and K, you can use the Wilmuth model to produce the age-specific mortality rates. From that, use standard techniques to produce the big L's that you need for our life table, our relationships between the rungs of the age pyramid. Okay, I'll pause and take a breath, but the key is that two parameters are going to determine the mortality part. For priors, K normal 0, 1 actually works really well because it's scaled so that it's almost always between -2 and +2. 0 is kind of the typical value, the neutral value of it. So this is a perfectly adequate prior. For Q5, I am going to suppose that we have some estimate, Q5 hat, and this is rather arbitrary, but we assume that there's a 90% chance that the real Q5 is between half the estimate and twice the estimate. Rather arbitrary. It says that we don't trust the estimate a lot, but we don't think it's too bad. And this we could debate what parameter, what constants to put in here. But the main idea is center it around an estimate. Okay, so here's if Q5 hat was 0.025, that's 25 per 1,000 under 5 mortality rate. Our prior on Q5 looks like this, almost certainly in this range. And here are just some example draws of Q5 hat. Sorry, if you have a population for which this is your estimate, these are the draws from the prior of what person years might look like, those big L's, and what childhood mortality might look like over ages 0 to 10. Okay, the key is it's a low dimensional parametric model that can describe the parameters we need in a reasonable way. Okay, for fertility timing, the other part that we need, this is a simplex, right? It's a bunch of non-negative numbers that add to 1 for the 7 age groups. A standard way of parameterizing that is to take log odds relative to one of the groups, 15 to 19 as the reference group, and you get 6 parameters that describe the relative odd or the log of the odds for the 6 groups compared to age 15. And then what we did is we used the human fertility database, another one of these big data sets, to come up with basically principal components, if you want to think of it that way, or singular value, principal eigenvectors, however you want to think about it, where we can describe the age pattern of fertility across the 7 age groups in a 2-parameter, basically constants, which are kind of the average. And then here is, we add in beta 1 times this vector, which makes fertility later if beta 1 is big. It raises the log odds of late fertility by adding bigger numbers to groups 5, 6, 7 if beta 1 is positive. And then another parameter that basically decreases the variance of the age of childbearing, beta 2. The big numbers are in age groups 3, 4, 5. Higher beta 2 is, the more fertility is concentrated in those age groups. Okay, and we just rescaled them so we get very convenient 0 means and variances of 1. And our prior will be that these betas have a independent bivariate normal, independent bivariate standard normal. Okay. So these 2 fertility parameters, beta 1 and beta 2, are going to tell us about the shape of fertility and how much of total lifetime fertility would have happened over the last 5 years for a bunch of women in the age groups that we see in the age pyramid. And here are just some example draws from the fertility shape prior. And remember, this is all proportions. The area, or all of these sets add up to 1. Sometimes we have late fertility, sometimes we have early fertility. This is calibrated to sort of act like the variation in high quality data. Okay, and just to sort of before we go on to the applications, to sort of remind you of the whole structure here. The key variable of interest is the total fertility level. It's unknown. But to get it, we need a fertility age pattern, which we're going to parameterize with these two betas. We need a mortality pattern, which is frankly a little less important in a lot of contexts, low mortality contexts. But if you give me a under 5 mortality rate and this shape parameter K, we generate a mortality schedule. Together, those give us expected children per woman. We know the number of women from the age pyramid. And so we expect the number of children that we count in the age pyramid to be a random result of those rates, so to speak, and the number of women. Okay, and we use a Poisson to describe the number of women that we observe. The likelihood is Poisson. The prior for TFR is flat. Prior for beta 1, beta 2 is standard normal, independent. And then we have the distributions I described for these two mortality parameters. Okay, and then you look at the posterior of the TFR conditional on the age pyramid. Okay, I'm going to talk through a couple of applications. The first ones are from a couple of papers, TFR for small areas. So if you have reliable age sex counts for small areas, you can use this method to estimate TFR even in the absence of location-specific birth registration. It might be possible to do this for historical cases when you know the population by age and sex, but you don't have any kind of vital registration, or for these other cases where you would never have this kind of information on a birth certificate, at least not in most places. Okay, and then last, probably the most interesting one is total fertility rate for super small populations. Okay, first, small areas. This is just a proof of concept more than anything else. Georgia has 159 counties, which is a lot for a state its size. Across those 159 counties, children under 5 vary from 96 children to almost 63,000. The population of women in the local age pyramid varies from 335 at ages 15 to 49 to 250,000. And there's a very wide range of NCHS estimates of county level under 5 mortality, some rather alarmingly high for the United States. When we apply this model to every county's population pyramid, this is what we get for the posterior medians. A range from the low 1s to the high 2s for TFR, almost a 2-to-1 variation, with the low values being in university towns or university counties, more accurately. 1.4 in the location where the University of Georgia is, 1.7 where Georgia State University is, and then we found 1.6 where there's a women's prison. The age pyramid for this county has an awful lot of women and not very many children. That's because not very many of the women gave birth in the last 5 years. We also found low fertility in the Atlanta metropolitan area relative to the suburbs, which makes some sense. And then particularly high fertility in, I believe this is Chattahoochee County, which is where there's a very big Army base. And you can imagine that there are sort of young Army wives who are more likely to concentrate their childbearing while they're living there and have, probably better support services. Okay, second example, we can take European countries for which we have population pyramids and go way, way, way back beyond what's in the human fertility database. I want to highlight this. This is data from the human mortality database, which has age sex pyramids for all of the, for France from about 18 1730, it looks like, for Sweden from 1748 or whatever it is, and so on, right? The segments to the right of the dashed lines are where we actually do have birth registration and fertility data. These are the estimates from the human mortality database compared to the estimates from the human fertility database. And you see we do fine. But then more importantly, we can go back in history much, much earlier for the years where we have age pyramids, but no fertility data. And there's a little bit of an advantage here. There's something called the Human Fertility Collection, HFC, that does have some estimates for these years. We track those quite well. And then there's, years before that where these are the sort of, these are new estimates in a sense, right? And we get all sorts of interesting patterns to explore that would not have been accessible if you needed the original formula to estimate TFR. Final basic application, we can look at fertility by income in data sets that don't have any fertility information at all. This is from the current population survey of the United States, which I don't think has a fertility question of any kind. We simply use the household composition of white household heads and non-white household heads, disaggregated by income, and found these interesting patterns of total fertility by race and income. Sort of a U-shape. You can imagine that as you get to really high incomes, you're more able to pay for childcare, nannies, more likely to be one income families with a, super high earner or something like that. Anyway, this is also new data or new estimates that you couldn't do without an alternative method. Okay, so to intermediate conclusions here, you can estimate TFR from the age pyramid. That's not really new. People have thought about that prospect for a long time. And the most obvious thing in the world is to say, if there are a lot of children per woman, fertility is probably high, right? But what we've done here is we've operationalized it in a careful way. And these kind of marriages of what are really indirect methods, you're not measuring fertility events, but you can measure their residual, which is surviving children, seem like a really good way to go. You can work out the formal demography. You have these big data sets that you can sort of build priors from. And then you can, in a principled way, incorporate what you do and don't know about the parameters to say what you'd probably, I should say this more carefully, what you do and don't know about TFR. Oh, sorry, I skipped that. And of course, as with all Bayesian models, we automatically get uncertainty estimates out of them. Sorry, I didn't say that. Okay. Maria, if I can ask you a question, how are we doing on time at this point?
Great, it's about 1 o'clock. So, and it's fine to go to about 1/4 after.
Okay, all right, I think we're doing great.
Mm-hmm.
Okay, the second and much more elaborate application, and this is, as I said, sort of an unfinished paper still, is this work with Marta Azevedo, who I'll describe in a moment, and Joe Potter at the University of Texas. Marta is a Brazilian anthropologist who lived in indigenous areas, by herself for many years, then later became effectively the Brazilian Minister of Indigenous Affairs, briefly in the Dilma government. Anyway, she's got a lot of on-the-ground knowledge, and she's also a trained demographer. And she lobbied the Brazilian Census Bureau to do better in counting and enumerating and reaching the indigenous population in Brazil. And as a result, we have new data, new in quotes now, from the 2010 census that allows new estimates of fertility. Okay, so what we're producing here is the first ever estimates of the fertility levels for several hundred indigenous territories in Brazil. As an anthropologist, Martha is particularly interested in how culture affects indigenous fertility. I'll describe that in detail in a sec. Just some background, in 1500, when the Portuguese arrived in South America, the estimates, and I trust Martha on this, about 1,000 different ethnicities of indigenous people, and a population estimated at about 3 million. In 2010, when the census happened, 305 countable ethnic groups, about 1 million indigenous people. That's about 4 out of every 1,000 Brazilians who are indigenous. And some of these are extremely small. Some of these are just handfuls of people, as I'll show you. But we would like to estimate fertility for all of them. Okay. Part of what we use is a model of borrowing strength across cultures. You can sense the anthropological or the anthropologist's influence here. What we decided to do is use the language structure of indigenous peoples. There are 2 main language groups with lots and lots of people. One is Macro-G and the other is Tupi. Those 2 groups constitute probably the majority of indigenous people. There are large numbers of indigenous peoples who have switched to speaking Portuguese only. So we're calling these Portuguese speakers, but we're disaggregating them by their sort of ancestry. And then there are a lot of like unclassified languages, sort of, unique. There's only one group that's known that speaks that language. That includes the Yanomami, who are a very big group, and you might have heard of. So what we have are these 4 major categories of indigenous languages. Within each of those, we have language families, and then with each of those families, we have individual languages. And we're going to use this as our sort of map of how to smooth or how to borrow information about fertility across peoples. Okay, Martha, I don't want to do this injustice, so let me just say one of the main differences in indigenous culture in Brazil is whether married couples move to the wife's village or the husband's village. There's always cross-village marriages. In some societies, the couple moves to the wife's village. That's uxora locality. Uxora is the Latin word for wife. Or vira locality, that's moving to the husband's village, vir being the Latin word for man. And then there's also linearity about how you keep track of whose family is which. And then there's also differences that are important in how the group sees how desirable the group sees increase being, and then whether they're sort of eager participants in the formal education and the national education system. All right, to give you an idea of where these people live, the answer is everywhere in Brazil. Another interesting fact is that they are sort of mixed. In the central Amazon here, we have both Macro-G and Tupi people. A spatial map, a spatial approach might not work well here. I guess a couple other things to point out. Portuguese-speaking groups are primarily concentrated in the Northeast and along the Atlantic coast. And then there's a very interesting area here. By the way, Maria, I'm going to ask you again. Can you see my cursor? I hope so.
Yes, you're doing a good job. I can see.
Good. This area here includes both Tupi and blue peoples and other peoples, orange and red, and other and mixed. And the Tupi are the Uxora locals, with the couples moving to the wife's village. The other groups are virolocal with the husband, with a couple moving to the husband's village. And that's going to be this will be an interesting test when we estimate the TFRs of whether that matters. Okay, because of my co-author, Marta, we have improved questions on identity in the short form questions that the Brazilian census asked in 2010. And even more importantly, we have census geography that is now aligned with the indigenous territories. Before there were overlaps and gaps and so on. And now you can identify an indigenous territory by aggregating smaller administrative units accurately. As a result, we're going to focus on those indigenous territories, which are legal constructs. Virtually everybody that lives in them is indigenous. We can identify their location from census geography, and we know that most of the people whose fertility we're interested in live in these territories. Okay, so what we're going to do is apply that age pyramid technique. They don't ask enough questions on the long form question for the Brazilian census includes fertility. Did you have a birth in the last year? But because these indigenous groups are so small, you only get an extremely small number of direct data points on fertility. But the 100% data does include the age pyramid information, age and sex. Okay, so we're just going to apply this, but with a couple of differences. We're going to add literacy as a covariate, because that is actually on the 100% data. We know children, we know women, we know literacy. We're going to estimate the TFR the way we did it before, but including literacy as a covariate. Okay, so we're going to use the model described earlier, the same structure that we used for Georgia counties, for example. We're going to add a cultural hierarchy, basically, and literacy as a covariate. And then we're going to do the same thing. We'll just look at TFR posteriors, conditional on the observable data for each of these 450 territories. Let me pause and let everybody take a break for a second. One of the main steps here, and I guess this is an important thing to acknowledge for demographers, is that you can't do this without knowing who lives where. And you can't know who lives where without anthropological and sort of, boots on the ground kind of knowledge. So we got anthropologists to look at the list of all 400 and something territories and tell us which people live there. And this is not a trivial step. This took a long time, right? Then the second part, which you can automate, is figure out which census sectors belong to a particular indigenous territory and add up the census data. So step one, slow, boring, requires an incredible amount of expert knowledge. Step two requires, R and a spatial package. Just give you a quick example. This is one indigenous territory called Aripuanã. The people who live there speak a Cinta Larga language. They're in the Monde family, and that's a Tupi group. And we call these trunks, families, languages, and territories. Just for a sense of scale, that territory is a significant, the area of that territory is a significant fraction of Washington State's area. And there are only a couple hundred people living there. And I'll show you the data when we add up the census sectors. These are the 14 census sectors that overlap the territory. You'll see I lied a little bit. There's a little bit of problem there. There's a little bit of problem here, but you can pretty much pick out where Aripuanã is. Here's the age pyramid data that we're going to have. 55 young children living in this enormous area. 64 women of childbearing age, divided by age this way, where most of them are teenagers, or not most of them, but the most numerous group is teenagers. Second most numerous group is 20 to 24, and so on, right? And the literacy rate among the women 15 to 34 is 2/3. Okay, so what can we say applying our fancy model that we previously applied to Georgia or the CPS or whatever? Turns out the range of uncertainty is much, much, much wider, right? We can be pretty certain that the TFR is somewhere between 5 and 7.5. But that's already new information. We did not know even whether fertility was above replacement for this group before, which is a critical issue for groups that are trying to repopulate, in fact. So we can say with fair confidence that TFR is way above replacement. Okay? And this is just one territory. All right, when we do it for all the territories, we're going to use this hierarchical model where we give a grand mean. And then around that grand mean, we think there's some dispersion by language trunks, those 4 big categories. Then with each trunk, there's some family effects. And then within each family, there's some place effect, something unique to the territory. Okay, this is an improper structure. It's not picking levels, it's just picking correlations. And the key is, of course, that it's borrowing strength culturally, right, across these language family groups, not spatially. Okay, and when we do that, we see significant shrinkage toward cultural means, I guess is where you might put it. The horizontal axis here is the TFR estimated for each place separately. The vertical axis is the TFR estimated for each place using this cultural model. I guess I want you to notice a couple of things. First of all, notice the extraordinary range. It goes up to 14 or 13, right? And put another way, we found some Hutterites, we thought. But when you shrink the models and shrink the estimates using the cultural hierarchy, it turns out maybe the highest fertility rates are more like 10, not quite Hutterite level, right? So some of these super high fertility levels are from very, very small groups that when you try to come up with an estimate that's more plausible given other cultures, other culturally similar people, you get a lower TFR. It doesn't do much to the estimates in this 0 to 6 range or something. We can use the cultural effect estimates to learn something about indigenous peoples in Brazil. These are our 4 major groups. It turns out those sort of independents, if you will, and I don't know if you remember from the map, probably not, but these people tend to live in the Western Amazon on the Colombian and Peruvian frontier. The overall effect of being in that group was this sort of fuzzy circle, and then the individual family effects within that group spread out quite a bit, adding, somewhere up to 2+ to the expected TFR for a group if they're in that language family. Portuguese speakers tend to have lower than average fertility, Tupi higher, and Macro-J lower. And again, remember the Tupis are the Uxora local, the ones that go to the wife's village. The Macro-J are the ones that go to the husband's village. So it looks like there is probably a positive effect, or it's an association, I guess, with Uxora locality. Okay, this is all 450 TFRs sorted and stacked up and added with added uncertainty. You can see there's a lot of uncertainty about TFR in these tiny, tiny populations, but there's also some very clear real variation that we get. Notably, some of those Western places are very high. Some of the Portuguese-speaking places on the East Coast are quite low, it'll turn out. Okay, super quickly, these are the Portuguese-speaking, some of those, these are the Portuguese-speaking, they tend to be a little lower. These are the Macro-J, they tend to be kind of in the middle. These are the Tupi, they tend to be a bit higher. And these are the others, the unique ones, mostly Western, they tend to be highest of all. If we look at it spatially, we see low TFRs, these purple, these deep purples are 0 to 2. We see high fertility among some of the bigger groups, Yanomami, some of these Western groups, extremely high fertility, the 8 to 10s are concentrated out here on the extreme frontier, although there are a couple of other locations where there are significantly, very high fertility. And then interestingly, in this patch here, you might remember it's the Tupi speakers in the middle and the other people on the edges. The Tupis are the orange, 6 to 8, 4 to 6. They are the ones with the higher fertility. And the non-Tupi people are the ones with the lower fertility. Zooming, oh, sorry. We have these Portuguese speaking people with the lower TFRs. We have this cluster here where the Tupis are high and the others are low. Zooming in on that second cluster, the Tupis are basically in this circle or oval. The others are outside of it, and it's clearly the Tupi people that have the higher fertility, thus supporting Marta's theory that where couples move has a lot to do with fertility choices and timing of these indigenous women, that they're more likely to have births early and often if they're in places where their aunts and their mothers and so on are still around. Okay, so summing this up, because of the new data, we can do this new analysis. We also needed a new method, but the foundation of this was the new data. Indigenous fertility is a lot higher than non-indigenous in Brazil, and nobody knew that that was systematic until this approach. There had been many, sort of individual studies of individual indigenous peoples, but this is the first sort of global look at it. And indigenous fertility is really high in Brazil. Brazilian fertility overall is below replacement, and here we're way, way above. Okay, and then this sort of anthropological point is that this cultural borrowing model, it doesn't confirm, but it produces consistent results, suggesting that going to the wife's village is pro-natalist, is pro-fertility. Going to the husband's village is leads to lower fertility. So thank you. I don't know if I've gone way too fast or not. Hopefully questions can sort out lots of obscure points. I want to thank all 3 of the co-authors who were involved in all this work. I'm going to give you a little bit of extra stuff. And again, this is because it's being recorded. This is my contact information. So if you want to email me, follow me on Twitter, see what stupid things I'm saying on Twitter, whatever. Got a GitHub that has a lot of the code. It does not have the indigenous fertility code yet, but it has a lot of the other stuff. Or I have a website where there's a lot of data and code from projects. And then finally, this is literally just take a picture of it later. But if you want to look at the 2 papers that are kind of the basis of the method, these are the places to look. Snap a picture when you're watching the recording, type out the URLs, etc., or write me and I can send it to you. So thank you for your patience. And I'm ready to go with if there are questions.
Yeah, so any questions? There's nothing in the Q&A at the moment, but I have a bunch, but I don't want to abuse my position. So any questions? Okay, I just ask one while people are mulling it over. So in the context I work, as you know, more in say sub-Saharan Africa, there might be uncertainty. The population, the W's in your notation, might be either undercounted differentially across different age groups, or maybe you only have that information from a survey. And have you considered where if those things weren't observed, but rather you either have to model those, or it's limited information?
Well, I've thought about it, but I haven't done anything about it. I mean, I think that's an important point. Another important point is age misreporting, right? I mean, you've hit on a key point, which is that the foundation here is a belief that the age and sex data is correct, and that what's missing are these demographic parameters that you're unsure about. Okay, but of course, this is a structure in which you could add uncertainty about the count, uncertainty about the age classifications, and so on, right? But no, we have not developed that. It's a good project for someone else to do. Or I'm willing for someone else to do it. I should say. Don't claim ownership of that, but it's a great idea.
Okay, thank you. Just have one comment. One great talk, Carl. That's one comment. But any questions from anybody or comments?
I see something coming up in chat about.
Oh yeah,
Nathan.
Nathan, would you like to ask that question, Nathan? Sorry to interrupt.
Oh, okay, yeah, I'd love to hear from Nathan.
Maria is just unmuting. Nathan or Ethan both have questions.
Well, I see Ethan's question. I can answer that. I'm sorry, I see 3 questions in Q&A. May I just?
Yeah, go for it. Yeah, please.
Yeah, I guess people are being shy. So Nathan asks, how might Brazilian policymakers use these estimates? I can tell you my co-author's concern was literally about the survival of these indigenous peoples. As you saw, there are only about 1/3 as many now as there were when the Portuguese arrived in 1500. They are, in the very, very up-to-date context, they're concerned about COVID and other diseases that are sort of imported. And they're worried about whether, they're going to survive in the long run. So the very first chunk of information is, is the total fertility above the replacement level for the group? And of course, that depends on the mortality level. But in short, the very first thing is hopeful. Yes, fertility is above replacement. It looks like, these groups are not going extinct. Okay, I guess a second way that policymakers might use them is for planning expansions of indigenous areas. There's a super politicized process of marking out these territories and then assigning them legally to the indigenous groups. There are groups that don't yet have legal rights that are sort of, how do I put it, almost as if the government is considering creating an indigenous territory, and knowing something about the demographic behavior of the group might help with lobbying. I don't know, else could hurt, I suppose. There's intense land conflict, as you know, and so giving an indigenous group legal authority over a real big chunk of real estate generates all sorts of violence and conflict. I guess, Nathan, I don't want to pretend that, I'm going to change the world with a TFR estimate, but, it's information that's important for understanding the context of those political and economic decisions. Amy thanks me for the talk. I thank Amy for the thanks. And Ethan, do you want to ask me?
Sorry. Yeah, sorry for my delay. So Ethan and Nathan are both able to talk if they'd like to follow up.
I would love to hear from people directly rather than just read.
Okay, thanks, Maria. Yeah, it seemed like there'd be an interesting next step to see what could be gleaned from 5 to 9 year olds, given most of the fertility occurs at the younger ages, maybe before mortality has a huge effect. So do you have any plans to maybe go back a couple more decades?
Yeah, I've experimented with that. Yeah, I know I've experimented with that. And the point Ethan's raising is excellent, which is that, well, 5 to 9-year-olds tell you about the fertility of women 20 to 54, 5 to 9 years ago. And 10 to 14-year-olds, et cetera. You've got a little window on more than just the last 5 years through the age pyramid. I have experimented with it, and it seems to work really well for Norway, but I'm less confident about other places. There's something really important that has to happen that I've left implicit, which is women have to be counted in the same population as the children. And the mothers of the children have to be counted in the same population as the children. Okay, so once you get to 10 to 14, you might have more separation, that maybe the child has gone off to live in an urban area and the mother's still in the rural population that you're trying to estimate the fertility for, right? The older the kid is, the more you worry about the implicit assumption, right?
Yeah, in my mind, I'm thinking about closed populations. I'm especially interested in the possibility of reconstructing historical populations and being closed or living in isolated. So in my mind, I'm thinking about how this relates to the methods being used in paleodemography.
There's a closed assumption. It's better than a closed population assumption here, because if women and children stick together and they both leave the population, go to some other village or whatever, then you do not have a bias problem, right? Well, actually, I should say this carefully. What this estimates is the recent fertility of the women who are currently in some category of interest. Okay, so if you think, for example, think of a case where as soon as you have a kid, you move out of central Atlanta to the suburbs, right? That means in the age pyramid, we're going to capture extremely low fertility among, conditional on living in Atlanta at the end of the period. But we're going to get higher fertility conditional on living in a suburb at the end of the period. For paleodemography, I guess I'm not as worried about that, but you have to be clear on what the kind of the question that's being asked here. And it's a little bit different than traditional. We usually think about conditioning on the state before possible fertility, but here we're conditioning on the state after marriage.
That makes perfect sense. Thank you.
Another simple example is if out of wedlock childbearing is completely forbidden, then you might only see married women having children in the age pyramid, because children cause marriage, right? I mean, so I guess what I'm saying, children may cause migration, children may cause marriage, and you're looking at the final state, not the initial one here. Did that help, Ethan?
Yeah, that actually makes great sense. Yeah, that actually you don't really need something as restrictive as a closed population, as long as the births and the mothers are observed at the same time.
I'm sorry to put you on the spot, but how might one use this for paleodemography? Like, are there reasonable age sex counts or estimates?
Yeah, I mean, I'm glad you asked. So I had this kind of long-standing desire to use some of the information on age structure of the remains from Pompeii that have been excavated. So there's kind of cross-section, which I think has the benefit of having a pretty, as I understand, a wide age distribution in it, and be able to reconstruct not just mortality, but also fertility estimates from the measurement of the cavities, which have been kind of assigned genders and ages.
Oh, I think that's super cool. Sorry, that's not very professional reaction, but wow, that's cool.
Carl, we're a little bit over.
Okay.
Adrian's been waiting. Would it be possible to do a quick response to Adrian and then move on to the student meeting?
Fine with me, I guess.
Okay, Adrian.
Hi, Carl. Terrific talk. Really enjoyed it. So it's a more general, maybe higher level sort of question about spatial correlation in demography. And I thought your point about your treatment of the cultural hierarchy was really fascinating. And I think it's natural to think about spatial correlation in terms of distance, which is John has done great work on mortality, for example, in that. But it's not so clear that that's appropriate for social science. And so you showed the cultural dimension is more important, or than the spatial component, or I wouldn't, but at least it's important. We found, for example, when we looked at total fertility, subnational total fertility rate, we found distance is not very important. Being in the same country was extremely important. So there's a very different nature of correlation, which is induced by the social structure more than distance. So, so I was wondering if would you reflect a little bit about the importance of the way to think about spatial correlation in demography more generally, and the extent to which distance is appropriate, or other kind of dimensions are appropriate.
Well, first of all, I'm thinking about just hearing your comment reminds me of that sort of very sharp line at the French-Spanish border, even today, right? In total fertility. It doesn't, you could live on either side, it very much depends which side of the Pyrenees you live on, not that you live in the Pyrenees, right?
Yes.
I guess, I think social scientists ought to think broadly about proximity and in particular about sort of social and cultural proximity. I think demography pioneered that approach. The European Fertility Project explicitly used language, in fact, as a way to measure proximity when looking at fertility transition, right? So, I mean, I think it's incredibly valuable. I also think it's really difficult. You often do not have theory or data about what's relevant for the behavior you're studying and what proximity means. And then even if you do have a good theory, you may not have the right information to implement it. I mean, I guess all I can say is I think it's something to be very aware of, sensitive about. Not we should not just sort of use spatial models as if they solve every problem. I mean, I don't know about you, Adrian, but that occurred to me the very first time I learned about spatial models. But
no, with me it was the opposite. As a statistician, I tend to think about distance, and our ideas about spatial correlation come from geology and agriculture, and where we think about distance. But it was only when actually doing that fertility project I realized, distance is not really the best way. It's not the dimension on which a lot of the correlation and influencing is happening. The national state seems to play a much bigger role.
Right.
Which actually, what you said about the Pyrenees, that dovetails with that exactly.
Anybody who lives in a college town surrounded by a rural area, like I do, realizes, no, there's no spatial continuity. I politically, culturally, economically, my college town, my college county is totally different from all the surrounding counties. Space is important, but I think we need to be sensitized and sensitive about, the limitations of using it.
Yeah, thanks very much.
Okay, well, thank you so much. That was a great talk. I appreciate you being here, Carl. And for John, thank you so much for inviting him, playing a role in moderating today. So I'm gonna say goodbye, but remember, all the students, go ahead to the next meeting to learn more about Dr. Schmertmann's work and career, which would be very helpful. So
right, am I right that there's a separate URL for the next one?
Exactly. The link is in the chat for everyone. And if you do have any trouble, I can resend it to Carl. It's in your email and some other places, but we can help with that. So again, thanks everyone. Appreciate it. We'll see everyone else back here next week.
Thank you very much, Carl. Yeah, hope to see you soon. Cheers. Take care.
Thanks to all of you.
Bye-bye.